Bonjour, bienvenue à tout le monde. Merci d'être venus aussi nombreux en cette dernière après-midi. Vous allez être en compagnie de Martynas et Elisa Chiapponi pendant à peu près 50 minutes, je crois, sur le sujet des webbots, à savoir s'ils sont nos meilleurs amis ou nos pires cauchemars. Voilà, je vous laisse en leur présence. N'oubliez pas, je ne sais pas si... Non, là voilà. Il y a Open Feedback sur le site de Riviera Dev ou sur Open Feedback directement pour aller mettre des commentaires sur la prestation, vos appréciations, etc. C'est très important pour l'orga et pour les speakers. Merci à eux. Bon talk.
Merci. Okay, hello and welcome everyone to the session where we'll discuss about webbots and raise the question, are they developers' best friend or worst nightmare? And we will give overview about how in Amadeus we fight back them. This is part of the project so-called Rescue, Resilient Cloud for Europe, and is financed by German government, thanks to them, and that's why session is in English, because I'm coming from Germany this time. So just a few words about ourselves. So we present Amadeus. It's a company that provides solutions for the travel industry. And you will meet Elisa Chiapponi today, that's cybersecurity researcher, and myself, Martynas, Buožis, who is information security architect. We both present global security operations team, where we are responsible for the security, and one of the main assets to protect are web domains used for the booking in airline business. So what are bots? Bots are actually scripts or services that do persistent tasks automatically in the web, and they are just useful or not useful tools. It depends on who is behind them and who is using this tool in which manner and approach. So if you look at the good bots, a good bot examples is like indexing content, like Google, who is indexing web assets and provides you ability to search the web and to get access to the information. Or it might be bots that are sending updates, like for example, news, weather changes, maybe stock changes and other information. Other example is automating tasks like updating social networks with new content and new information. However, on the other side, we have bots that are called bad bots, and they provide certain kind of attacks, like phishing attacks, account takeovers, financial frauds, and they're used by the bad guys to provide something that is under the bad activity. In addition, even good bots, when they are abused, when they are utilized in a high manner, they might create also a denial of service, and their good bots also shall be used in the manner that it's controlled. So the tendencies, as you see by statistics in 2024, it's that bot activity is taking 51% of the traffic in general, and it shows that actually bot activity is becoming internet itself, because the less traffic is generated by real humans behind. And bad bots activity now is 37%, and you see in statistics, every year it grows by 4%, and this is an increasing daily risks that should be well managed, understood, and fight up front. It's coming. So some examples about functional abuse attacks. We'll talk about the services that companies provide as a service for their companies in e-commerce world, but they are abused also, can be abused also by bad bots and threat actors. So one of the examples. Okay, is it better now? Sorry. Okay, one of the examples is that companies provide to the customers ability to book services but not buy them, just put them on hold and reserve, but do not pay them. So it's convenient for usual users, but might be abused by the bad bots and bad guys, because they can put a lot of on-hold items in reservation, but they are not paying for them. What type of the impact does it have? So disrupt supply and demand. So bots are generating demand for the reserved assets. And this leads to the company to the decision to increase supply. And of course, this also went to the impact to revenues and operations, because you have a lot of assets in reservation, but you have no payments because bots keep them on hold in the cart. Another example of misuse of this is defeat the competition, because the competitor company might just do attack against company, and they can put all assets on hold, and you will not be able to buy anything. And of course, you will go to the competitor because they will be providing you services to buy assets. In airline business, it's holding a cheapest fares called seat spinning. It's actually when bots just put on hold on the reservation the all cheap tickets, and they become not available to be bought. Of course, this increases the tickets that can be bought further, because airlines has business approach that the less tickets are available, the higher price goes up. So to explain the impact, so you see that for the company impact, that requests are going up highly without any purchase behind and not generating revenue. And this generates an impact to the reputation of the company. Because if you can't buy cheap tickets or you can't buy any asset at all, you lose reputation, and of course customers are going to the other company that provides services as expected. Another example is called SMS pumping, where a company provides services for you to give a phone number and to get some information, like it might be, for example, one-time password. How this is utilized, so it impacts revenues for the company, and they generate revenue through network operations for the bad guys, because usually they request to send SMS to so-called VIP numbers that have higher prices to be served, and they get a revenue through network operators, and even in some cases they work together with network operators to gain more money. So of course it has impact to the revenue and the reputation. Just for example, imagine that you want to get access to a bank account, you want to get a one-time password to log in for multi-factor authentication, but you are not available to go through because the service is under heavy attack by bot and your SMS is not going through. So how do we protect our servers and websites from malicious bots? So it's called arms race game all the time happening, because website always invents a detection technique by bots to block them. However, the bad guys always find a way how to bypass detection techniques, and this goes in rounds, that sites, legal websites, shall invent new methods about how to detect bots and how to fight back. So a couple of examples, it's browser fingerprinting, where if browser fingerprinting was implemented and human fingerprinting was implemented, however, bad guys bypass this technique by using browser emulation frameworks. Then the next step was to invent JavaScript cookie challenges. However, bad guys bypass this technique by automated browsers that we manage to process cookies and behave as a human being. The next step was to implement CAPTCHAs. I believe that you almost daily have to solve some CAPTCHAs, like to enter some data information or to select pattern of the pictures to prove that you are human beings. However, this was bypassed by the CAPTCHA farms. CAPTCHA farms are, for example, human beings settled in maybe in low-income countries, where bots who are not able to resolve CAPTCHAs themselves sent to a set of human beings to resolve CAPTCHA, and they use this to bypass a technique of the bot detection. And so to mention, today it's easier to have access to evasive bots, because even if you are not very experienced in scripting, you can ask artificial intelligence tool to generate for you a bot, like for example, Python script that will bypass bot detection techniques at the website. Or you can even use services, so-called web unlockers, where you pay a rent and you don't need any kind of understanding about coding or scripting, where you get a bot detection technique bypassed by paying amount of money. So the question is actually why we cannot block bots by using IP addresses, and this comes to the evolution of the IP address protection. So initially it started with one IP address, and of course it's not a big deal to block one IP address and to say that this IP is malicious. However, this evolved to the certain techniques, like bots start using a data center. In data center you have many IPs available, and based on the service you can rotate IPs and change them. This evolved to the building blacklists of data center IPs, because it's clear that data center is a servers behind, not a human being behind. So by building blacklists for data center IPs, the next iteration of the detection bypass based on IPs is malicious botnets. Malicious botnets are actually human devices like laptops. They are infected and they are compromised, and they are used by bots to bypass the IP block technique. However, this evolved also into the blacklists, because initially human-based IPs were whitelisted. However, this evolved also to the huge list of the blacked IPs of the assets that are infected. So, question is, what comes next now in our world? And this is about residential proxies. And Elisa will continue introducing to how we use network measurements and IP intelligence to fight back this in Amadeus.
Thank you. So, who knows what residential proxies are? Okay, a couple of people. So we will call also them RESIP in short, and they are large networks of residential devices such as smartphones, laptops, tablets that we own. So they are owned by genuine users such as you and me, who share, ethically and voluntarily or not, their usage with these companies. The problem at the website is that there is no application layer information when a request is proxied by these devices. So the devices sending a request directly, or when they're using as proxy, basically send the same request, and for traditional bot detection methods, it's indistinguishable. And these also create a high probability of false positives when we use traditional detection methods, which is something that in business, such as the one we have in Amadeus, we don't want, because we don't want to block someone that could actually buy something on our websites. And lately, advanced bot traffic heavily rely on residential proxies, and as we saw, there is a lot of traffic in the internet, so you can imagine the amount of bot traffic through residential proxies that we see. So the attackers have different advantages. First of all, they have access to tens of millions of residential IP addresses, and these IP addresses should have a good reputation. We'll see in a bit why I don't say really good reputation, because there are some cases in which it's not the case. But these IP addresses are IP addresses of devices that we use every day to do things, and also they're not mainly, in theory yet, used to perform abusive actions such as malicious botnets, and so they're not flagged as malicious in reputational databases. Moreover, the attackers this time do not have to build a private distributed infrastructure such as a botnet. They can just really buy the services in these residential proxy companies that you can easily find on the internet. And there is no direct traceability, because multiple actors can be behind the same residential proxies and do the same campaign to one website. So it's difficult to discriminate between the different campaigns. So we said that these proxies have access to a large amount of devices all over the world. And these devices are owned by normal people, such as you and me. But how do they do that? So some providers have other applications that are not branded with their brand usually, in which they give you free services, such as VPN. Of course, if you read the terms of service, you will read that when you're not using your device is used as a proxy to proxy out information. But not everyone actually reads the terms of service when downloading an application, so we have an issue there. Then we have other cases in which the application clearly tell you that your device will be used as a proxy, and they pay you for the amount of bandwidth that they use from your device. This, however, can be illegal in specific countries because this practice is not always allowed because you're reselling the bandwidth of your network operator. So depending on the country, this can be illegal or not. Then we have mobile SDKs provided by these parties that can be included by app developers in their app. And in this way, app developers get a percentage from the number of downloaded application with this SDK. So again, probably it's written in the terms of usage that the app that you download for doing Sudoku is proxying out traffic for you, but not a lot of people actually read them, and so users are involuntarily part of these residential proxies. And finally, as we said before, there are also IP addresses that show bad reputation because they're part of infected devices campaign, so botnets. There were proof of IoT devices and routers. So even if this company says that they ethically source their devices, we can see that it's not actually always true. So this company are legitimate company, as I said, you can find a lot of them online, and they all say that they are ethically sourcing, but they have a shady device recruitment because in most cases the users are unaware of having this software on their devices. Also, different research works from academia and industry show their involvement in different malicious activities such as credential stuffing attacks, cryptojacking, financial scams, phishing, and many more. And also, they are much more expensive than common VPN, because a point that I get raised many times is that, yeah, but they're just network that enable you to proxy out requests from another node in another geographic location, which is a VPN. However, if we check pricing, residential proxies are much more expensive than common VPN. For example, one provider can ask us $7 per giga in residential proxies, and we can have VPNs that for $6 a month give us unlimited traffic. So if we just want an anonymity, why shouldn't we use VPNs? And probably the answer is that VPNs check much more than they do not proxy out malicious traffic. And also that some VPN IP addresses are actually part of databases, so it's clear that they're part of VPNs. So for all these reasons, we can see that there is a high suggestion that a lot of malicious attackers actually use this technology to perform malicious activity. So let's see a bit in detail how it works. We have the original client that want to connect to a website through a RESIP, that is short for residential proxy. So they first send a request to the initial node called super proxy, and then one of the gateways among the available one at the time is chosen to proxy out a request and send it to the website. And as we said, there is no application layer information about being proxied. So we had an idea, and we said, okay, at the application layer we cannot do much. What about the other layers? And specifically, what if we check the transport layer? And we do some network measurements to understand if there is a difference. So now I will explain something really high level. If you want more technical details, we can go through it during the questions later on. So let's imagine genuine users that want to connect directly to a website. It will build a transmission control protocol, so TCP session between the user and the website. And also, if we have a good website that use HTTPS, as any website should use, we will have a TLS session where packets are encrypted. And the TLS is built on top of TCP and take place between the same two parties. What happens in a residential proxy connection? We have a TCP session between the original client and the residential proxy, and a second one between the residential proxy and the website. And moreover, these two are not synchronized among them, so we really need to think about them independently. However, the TLS is virtually built between the original client and the website, because the TLS packets pass through the residential proxy network, but they're never decrypted and re-encrypted. So even if it passes through that, we can really think virtually that it's built between the original client and the website. Okay, so we see that there is a difference in how the topology of the sessions is built. Now the question is, how can we understand that with only the information we have at the website? Because when we receive a request, we actually don't see what we're seeing here in the picture. And the answer is using the round trip time. The round trip time is the time for a packet to go from the website to the genuine users, and for the corresponding packet to come back. So in a direct connection, the round trip time will be similar because the TCP and TLS session will take the same time. However, if we have a residential proxy connection, we will not have the same scenario, because while the packets will stop at the gateway, so at the residential device in the TCP session, in the TLS1, the packets will go on and arrive to the original client and come back. Okay, so we know this. Of course, this was our theoretical idea. We needed to check it into practice, so we did a 4 months experiment. And we understood that if the difference between the round trip time TLS and round trip time TCP is bigger than 50 milliseconds, we can say that the connection is coming from a residential proxy. We also needed to check if there were impacts on the detection technique. We checked if the packet speed, which is not constant all over the network, and TLS version could actually impact it, and the answer is no. Then we check the client processing time. So for example, if a direct connection is done through Edge or through Chrome, do we see an impact? And the answer is no. For specific browsers, there is an increase in the difference that we see among the round trip time TLS and round trip time TCP, but it remains below our threshold of 50 milliseconds, which was built to reduce as much as possible false positives. Then we checked the network delays, because we know that there are delays in the network and congestion, and also the geographic location of the parties, because our idea is based on the principle that the packets in the TLS residential proxy connection go to a much farther place than the TCP ones. So what happens if all the parties are really close in space? We saw that there is an impact in the false negatives, so some recipe connection will not be detected. But however, since there are multiple parties that handle the packet, there is still a difference in the timing that we can leverage, and so our accuracy remains pretty high. The main point we saw is that we have specific false positives for specific mobile carriers and VPNs that have a similar protocol in place. And so in this case, we need to whitelist them through their IP addresses and thanks to other parameters that enable us to understand if we're in one of these two cases, and put higher threshold there, because still they could be used as residential proxies, just we also see an increase in their difference even when they're not used like that. So our approach works request by request. So if we receive a direct request, we see that the difference is below 50 milliseconds. And if we get instead proxied requests, we see that it's above 50 milliseconds. And it's linked on the infrastructure management of residential proxies. So the question is, could they break it? Could they not be detected? The answer is yes, because they could just break the TLS session. So they should decrypt and re-encrypt inside the proxy. However, we think it's unlikely to happen on large scale, because if that would be the case, then at the residential proxy device, we would be able to see clear test what they're proxying out. And let's imagine that law enforcement would do that. Then they would see if there is any malicious traffic or any malicious activity. So for this reason, we think it's unlikely to happen large scale. And at the moment, we integrated this technique in our anti-bot protection solution that we use at the web application firewall. However, we said it's an arm race, so we need to be ready for the next step. And we said that there are ways, even unlikely, that they could break it. So what about IP addresses? Because we saw, even in the case of malicious botnets, that at the beginning it was good because IPs had a good reputation, but lately they were so misused that the bad reputation grew on them. So in our experiment, we collected all the IP addresses of the residential gateways we saw. And so in the end, we had 69 million plus recip connection from 4 of the major recip providers. And we did different analyses that told us different things. So one thing that we saw is that each provider reuses IP addresses among different paths and possibly users, but less on the single path. So let's say that I use a residential proxies to connect to Amadeus.com twice. I will most likely have 2 different IP addresses. But if at the same time I connect to two different domains, like Amadeus.com and Amadeus1.com, the probability of having the same IP is much higher. This is important because it tells us that if we check different domains, we can see much more often the same IPs as part of residential proxies. Then we saw that some providers share their pool of IPs. And this is really important because imagine we have 4 providers and each of them have access to 10 million IP addresses. Then we have a total of 40 million IP addresses that we should check. But if 2 of them share completely their pool, then the total pool goes to 30 million. So it's a key information to have. And our results show that 2 providers share 92% of their pool of IP addresses and some others share up to 20%. So in total, the number of IP addresses is much smaller. Also, we did some mathematical modeling on the data we collected to understand if the values that this provider claim on their website, which is hundreds of millions of IP addresses, is actually true. And we saw that our results do not match what they claim. So we think that they actually don't have access to it and they overestimate the number of IP addresses that a same device could actually get. Because it's true. IP addresses change. Even if you stay in the same place, your network operator could change your IP address. But even if it changes, most likely you will get an IP address that is in the same /24. So if you have an IP address like 1234, the /24 is 123.0/24. So we have 256 addresses inside it. So most likely your IP will remain in the same /24. So can we capitalize on this information? The answer is yes, and our project is to track the /24 that are used by residential proxies and associate them with a risk score, because of course we cannot really just block them, but we can be more suspicious to the one in which we see many connections from residential proxies. Sorry. Also, we are aware that there are genuine users that share their devices with these proxies, so we need to whitelist them to reduce false positives. And so decrease the risk score in case we see good connections. So we did an analysis in Amadeus, and we took the traffic of 30 days in a domain that are representative because they have both traffic as in the other domain that we protect. Now we'll explain a lot of numbers. I will try to be as clear as possible, but in the next slide we also have some takeaways. So we had 3 domains of airline booking domains, and we can see in the second column the total number of requests they received. We have the first one in which we have almost 2 billion total requests, and the percentage of residential proxy traffic was around 20%. In the second domain, we have 105 million total requests, and 21%, 22 almost, was residential proxies. And in the third one, instead, we have a much higher percentage of residential proxies because we have 80.59% on a total request of 77 million. So we first check at level of IP addresses. So let's see in the first column, the distinct recip IP addresses. We can see that we have different scenarios. In the first domain, we have almost 12 million. In the second, 1,200,000. And in the third, almost 5 million. Let's see in the first 2 lines, the average number of requests, median requests, and max requests. We can see that the average is higher than what we see in the median, and by far. So what it tells us, since the median tells us where it stands 50% of the request, it means that there are some IP addresses that make a lot of connections and so move the average up. And we can see actually that in the max request, because we can see that some IP addresses in the 30 days, they did many requests, 13,000 and 16,000. Instead, this is different for the third domain, in which we have less difference between the average and the median. And indeed, the maximum number of requests is much lower. It means that in this case, each IP address was doing less, a more consistent number of requests. One thing we wanted to check is the minimum interval time among requests from the same IP address, because we thought, what if at some point in time the residential providers just have access to a limited amount of devices, and so they repeat much more the IP address even between the same domain. And this data actually show this to us, because in the first two cases the interval is kind of low, 2.3 minutes and 1.2 minutes. And instead, in the third domain, it's much larger, where the IP addresses send a more consistent number of requests per IP address. Now let's consider the /24, because that's what we said we are interested in. So first, we need to check with respect to the distinct number of residential IP addresses. We can see that there is a clear difference between A1, A3 together and A2. Because in the first and third case, if we compare the number of distinct IP addresses and distinct /24, we see that the number of /24 is a bit more than half of the distinct IP addresses. Instead, in the second line, we can see that we had 1,200,000 distinct IP addresses and only 353,000 /24. It means that all these IP addresses were from less /24. So we should track less /24 if we look at that. Also, if we check the average number of requests, median and maximum request, especially in the third case, where in the IP addresses we had a difference, we can see that now the average is much higher, and also the median, and also the maximum number of requests. Indeed, we have 7,863, and before we have 546. So it tells us that if we check the /24, we can see many more requests from the same /24, and also the average and median increase, which is something expected because we are grouping together, but still we have a large increase. And again, we check the minimum interval time, and for the second domain, where we have a low number of /24, we see that we see those same /24 really close in time, 0.5 minutes. Another point that we raised before is that from different domains, so we should be able to see more matches. So let's check that. And first of all, let's check the pair A1, A3. In this case, we had a really big percentage of shared IP addresses, 1,700,000, which resulted in a lower lower number of shares /24, 1,500,000. And this is due to the fact that the IP addresses matches were really high, so they were part of the same /24. Instead, in the other case of the pairs A1, A2, A2, A3, we see that we have a lower number of shared IP addresses, but a bigger match number of shared /24. And this pattern is, again, the same if we look at all domains together. Only 240 IPs were shared among the three, but if we look at the /24, we have 135,540. So, as I said, a lot of numbers. But let's recap. What does this data tell us? We have a small number of /24s that generate large amount of traffic in recipe requests. So this tells us that most likely some devices with IP reallocation remain in the same /24 as we said before. Also, in small interval of time, we have a high probability of seeing the same recipe IP addresses, and this possibly depend on the provider they use and the availability at the time of residential devices they have. Then we saw that the majority of /24 generate less traffic, but if we compare traffic from different domains, we can see which one are more malicious and assign a higher risk score. So in general, this information tell us that analyzing traffic confirms that we can use the /24 patterns to build risk score and possibly identify residential proxy connections. So of course, we said that we want to maintain false positive load. And so we studied that. We checked for the studied domains if any booking was performed the same day the IP of /24 was being part of the attack. and that didn't happen. However, if we look at the 30 days period, we see that those IPs and /24 were used to perform bookings, 1.2% of the total IPs and 4.5% of the total /24s. However, we saw that there was a difference when we saw the IP address and when we saw the booking, and the minimum number of days difference between a booking and an appearance as an attacker was 6 days. If we look on the industry, most commercial reputation databases actually use 3 days to flag an IP as malicious, and after 3 days, if it is not part of an attack anymore, the IP is not considered malicious anymore. So if we would follow this industry best practice, we should not have false positives. However, this was just a proof of concept on a small number of domains. So our idea is to implement this system to cover all protected domains and test the false positive rate on large scale. So this was all. I will recap a bit what we said today. First of all, we saw that a large share of today's internet traffic is made up of bots, good and bad. Bot traffic, malicious one, can cause financial loss, reputational damage, and service disruptions. And even beneficial bots can negatively impact websites by overwhelming them. We saw that residential proxies are leveraging bot attacks, evading standard defenses. And we saw how we detect them at Amadeus through network metrics and customized IP intelligence to provide protection while we maintain a low positive false rate. So this was all. Thank you for your attention, and we would be happy to take any question. Please. Okay. Mm-hmm. So we use really the protocol as it is built. So in the case of the TCP, we take the timing. So it works like that. The client sends a SYN, the server sends a SYNAC, and then we send an ACK. And we take the time from when the SYNAC is sent to when the ACK is received. Instead, for the TLS, we use, depending on the version of TLS, we use different messages. For example, in TLS 1.2, when there is sent the server hello done from the client, the protocol does not allow the client to send any more packets until the server sends a message. And so we take the time from those two. Okay. Sure. So the TLS is the longer one. So in that case, they would like to be faster. To slow down the TCP, the answer is no, because this part is handled at the kernel of the device, which is at the transport layer. And the attackers do not have actually access to the physical device, so they can just work at the application layer. So they cannot change that. And so this part, no. They could try to have a smaller round trip time at TLS layer, having all the parties all together, as we saw in one of the slides. But then it became a problem of, then you have to have a distributed network yourself as an attacker. Sure. Yeah. So we did some market analysis on the internet. At the time of the study, which was 2022, we checked which were the websites that were appearing the most, and they were also more picked up by industry reports, and we made a choice among them. But these were these are the main providers. They are also the one that advertised to have the larger pools. So we strongly believe that they're representative. This could have changed. Now there are many more providers. Before, like 3 years ago, there were a bit less. So the answer could change. Yeah. I take it? So, I mean, it depends a bit on the bots. Not all bots are really sophisticated and use residential proxies. So there are scripty kids that with one IP, they send a lot of requests. So we have those detection in place because, of course, like you don't expect just the really sophisticated ones. What we talked here about are the really big ones. The other, we block them because we see that there are data center IP addresses, so we block them. I don't have statistics now.
I think in short to say with every iteration of the IP detections, the dynamic of IP changes is increasing. And with residential proxies, we have even huge dynamic than with botnets themselves. So we have a larger scope to address and to find out and to dig up which is a bad bot.
Sure. We try not to because we do many analyses before blocking. If we're unsure, we put, for example, CAPTCHAs or we put other mitigations before blocking directly because, of course, we don't want real user to be blocked. Yeah, sure. So you mean residential proxies or other VPNs? Okay, so you say if we have a real person that just use the residential proxy to connect to the website, and if someone is doing an attack? Okay, so usually we start to block when there is an attack ongoing. So if there is just one single person that uses a residential proxy, usually we don't block it. It's more when there is a large volume. I find the scenario a bit unlikely because, as we said, it's much cost effective to use a VPN. It could happen. Then there is also a business decision to understand if we're fine that real user use residential proxies or not. So I think it depends a bit case by case. For the moment, I don't think we got any alert that we blocked someone that was using a residential proxies and they complained. Yeah, because actually, so the scenario explained is a bit simplified, but the residential proxy that we find on the internet usually do not get the pool of IP addresses themselves. These are like two separate companies. So we have the company that sells to the attacker, let's say, and the company that serves the proxies. So two same company that sell to the client attacker could actually refer to the same pool of IP addresses. And we did also some experiment in other papers we published on that, and we saw that it's the case. Like there are more end user providers that rely on the same provider for the IP addresses. What do you, when and like for residential proxies or not? No, our idea is to have a dynamic risk score. So not to, I mean, it's really difficult to just block the IP because it could be a real person behind it. So to be more suspicious, and so if we see that there is a large amount of traffic from suspicious /24, then we could block or put CAPTCHAs or other mitigations. And then if it's a really big attack, maybe we block, but of course, cautiously. Yeah. Yeah, because usually, so usually we try to have a really good granularity on what we block, especially if we block. we try to be really strict on the parameters because we don't want to impact many false positives. So we use this in combination with other parameters. Usually we use this to have a general view on the traffic, and then to isolate bot traffic, we use also other parameters. Sure. Yeah, we also studied that. We didn't see any specific patterns, and there were some repetitions sometimes. But it's also something we're researching about. Also other patterns in the application to try to detect it early on and to block it. So we are in collaboration with a third party that provides us the web application firewall, and they do that, the measurement. So I don't have this number. It's a good question. They didn't tell us, so probably it's not impacting, and they're also collecting a lot of other parameters. So I think it's part of the, yeah, probably it doesn't have a big impact, otherwise they would have told us. Thank you very much.
Thank you.